We're live. Live and direct from the piano lab. Here we go. Come on. Jesus. There we go. I have a question. Can you guess what makes up a person? So, the field of ionomics is the measurement of the total elemental composition of an organism. That is, we are all sitting here made of atoms, and one way you can think about a person is the ratio of one element to another. Who's done this? So what I would like, we don't have house points in this class. We're not doing that here, but you can certainly, let's break you into, no, it'll just be the whole class. Why don't you guys circle what you think are, let's do it like this. We'll have red be common element in the body, and purple be trace element. You just have to a little bit of versus a lot of. Yeah. Figure it out. Work on it together. That's it. Yes.
There's helium on the side.
Oxygen, hydrogen.
Oxygen.
Hey, whoa, guys. Okay. Something starts with a C.
Oh, where's iron? We need iron.
Iron is.
That's iodine.
No. Where's this one that starts with a C?
Helium.
No.
Your brain is.
You just inhale a balloon, maybe? One that starts with a C.
Oh, potassium.
Do we
Oh,
think there's a
cobalt.
lot of iron? No.
Potassium.
I don't think there's iron.
K.
K.
Give me the
K.
cobalt.
Cobalt.
Only 4 common ones? I can't. So, oxygen, I think that's.
Wait, only 4 common ones?
Is there only 4?
I didn't say that.
I thought there were 6.
Ashley is saying that, so I believe her.
I thought there was 6.
Ashley.
I thought there were 6.
Nickel.
I thought there were 6.
Oh, zinc. There's a lot of zinc. Not you.
What? There's 6 of them, I believe. There's oxygen, hydrogen,
Circling some
Wrong.
and one that starts with a C.
Potassium.
You're like
What about
That's a K.
Calcium.
That's potassium. Every kiss begins with potassium.
Sodium.
Poet.
I don't know which one starts with a C. I can't find it. C-O something.
You can't even read that.
If there's one, it's a main one that starts with a C.
Radium.
There's one main one that starts with a C, and there you go.
Copper.
There's one main one that starts with a C, and I
Oh,
can't
wait, did
find
you say
it.
Gold.
No.
gold.
Did you see that like fancy water like gold?
Okay, but I actually am trying to figure it
There's
out.
one that starts
Yeah.
with a C, and I can't find it.
Copperinium.
It starts with a C.
Thorium. I can't read that.
There's only so
Titanium?
many C's in there.
I know, that's why I'm find it.
Maybe
There's
it's
a CO.
maybe it's
Something
calcium.
that's-
You don't have chlorine in our water, or else
Oh,
I'd be able to
I'm
drink out of a
reading
pool.
all the C. I can't read that.
Oh,
No,
There's,
no,
there's
letters.
a few, I'll just
Chlorine.
There
I
are
don't know what that
Starts with a
Wow.
CO.
are
CO
missing
something.
that are obvious if you think about
CO something.
What?
it. There,
Wait, guys, what if you just like part in
Move, yeah, move.
There's no
actually-
C. There's one more, missing one. Wait, hold on. Where's the one that CO?
Girl, I have no idea.
Ugh.
Chlorine. Selenium.
I think it was.
I actually
That
think
was
we
it.
do have.
It's circle purple.
that's MN is manganese, right?
Manganese.
That's not magnesium.
No,
Did you get calcium? That's the one. No, CA.
that's
Calcium.
magnesium. That's
That's what I said.
manganese.
Where's calcium
It's over here, I
and...
got it.
Okay, where's phosphorus?
Phosphorus.
Phosphorus.
This?
That's the uncommon. Which one's the common one? Wait,
The purple.
the purple's common? No,
Purple
common.
is uncommon.
Okay, that one, that one, that one, that one. I don't think it's zinc. That's purple.
I have no idea. There's manganese or whatever you said.
4, 5. Hold on. Can I burn the purple thing?
Manganese.
That has to be purple. Where did we go? Zinc's purple. I don't know.
Zinc is
I know the
common.
red ones now. Phosphorus, oxygen, nitrogen, calcium, Carbon dioxide, hydrogen, potassium has.
Let's go down the list, everybody. Helium.
I think.
Probably not.
There we go. Awesome. Okay,
Ne.
Neon.
1, 2, 3, 4.
Probably
I
not.
think I did it. I think I did the red one.
Fluorine. I think that's what that
I
is.
think I got the red
Fluorine,
one.
yes.
Perhaps.
Wow, that hurt.
Question.
We'll put a question mark.
Okay,
What
let's do the red.
is the ionic fluorine?
Fluoride.
Fluoride.
Oh, yeah.
Wait, I don't think that's in the red.
Should we do that?
Fine,
No, it's
purple.
not purple. No, it's not purple. The six are the. Oh, yeah, it's not red. Yeah, it is purple. That's the common one.
You have purple, girl.
I'm sorry.
See, it's amazing how much you guys already know.
Oh my gosh.
Hardly
How
anything
about
is,
gold?
you guys. No,
Raise
no.
your hand if you
No.
think gold is.
That'd be fun.
Show of hands? Okay.
We're not doing gold.
Everyone who didn't raise their hand is poor. I'm kidding. I'm not a Republican. I don't hate the poor.
You can't say that.
Yeah, I can.
You can't
Copper.
say that. Jacob.
Who thinks
you
there's
gotta
copper?
apologize. That's not
To
nice.
who?
To any Republican, that's not nice.
There are none here.
I don't know.
Copper.
That's not nice though.
No.
Well, except for Lance.
That's not nice.
Copper.
Apologize to Lance.
Aluminum.
Then apologize to Lance, because that's not nice.
There might be aluminum.
Then apologize to Lance. 'Cause-
Wait, where's sodium?
I don't know.
Where's the salt?
Oh, and
in it?
Sodium is
I don't know. Yeah, that's not it.
Do we have it?
left.
Oh, here it is.
Oh, it's there. Okay.
I don't know what's
Lithium.
That's sodium. That's. Wait,
Yeah, there's loads. If you eat bad like me.
Wait, no. That's
Germanium.
what you put into your body. I don't think it's sodium in your body.
Tin.
No. I think we're good. We're done.
I think we have them.
Okay.
I don't think
One
so.
last question. There's one obvious one you guys are missing.
Is it red?
Have we said it?
Magnesium.
It's over.
I don't know where that is. Oh, here.
Yeah, that's not as obvious. As
I don't know.
It's not ours.
So-
is it?
what is one of the things that makes potato chips and sodium? Okay.
Chloride.
Yeah, sodium chloride.
Yeah,
What is
yeah.
sodium? What is salt?
Chloride.
Chloride.
Chlor.
There you go.
Yeah.
Okay, let's see. Let's see how you guys did. Are we done? Are you done? Is that it? Is that everything?
Well, I
Anybody
don't
else?
know. So we're in the way.
Ashley, you who have prepared and looked ahead, do you feel like you remember?
I remember
But-
some of the.
How would you adjust it?
Wait, hydrogen. What? Wait, what's the common one?
No, it's
Wait, which ones are common?
hydrogen, carbon.
And
Okay.
then there's no. It's not just that. It's the soft.
Phosphorus.
Phosphorus and calcium are also common. Wait, what's hydrogen?
Just
Wait,
tell
wait,
us so she.
Is the red
she
common?
know.
Huh?
Was the red common?
The red was common, yes.
Okay, got it.
You ready? Ooh.
Wow.
So, yeah, wow. I need to. That is not. I should have had it so. So yeah.
Circle all the ones that aren't in the boxes.
Well, no, I did. The like
it's all-
table is
okay.
not. Yeah, I
Okay,
should
now
have.
hold up. We got all the.
Oh wait. Isn't it shift? So it's.
The whole table's off. Let's see. I can probably fix it. Let's see if I can do it.
Okay, I was like,
Wow.
we got okay, but all those bottom ones.
Yeah. See this.
Oh, actually.
Yeah, the table is screwed up. So let's.
We're really messed up on it.
Oh, I see. I see what happened.
Did we do that? Did we
Yeah, I should have. Yeah, I know. I'm just doing it for next time. Okay, whatever. So
That's it.
let's see what we got here. You guys did pretty well. You did pretty well. Yeah, you did pretty well. You missed a couple important ones. I know. I'm just erasing it because it's all crazy now. You missed, importantly, iodine. Iodine is essential for the thyroid to function. You need iodine. Like, that's why we iodize salt. You've seen that word before, iodine. Iodized salt was because people that lived in the Midwest who didn't eat fish that came from the ocean, which naturally has iodine, they would get what's called goiter. Heard that term, goiter? And it would be this thing where their necks would have these like hypertrophic thyroid because they didn't have iodine in their diet. So they started iodizing salt, replacing the chloride ion in sodium chloride with iodine. So that's an important one, but it is trace. And there is like these other things, a little bit of tin, selenium, cadmium, molybdenum. You need just a little bit of it, just a tiny bit of vanadium. Just a tiny bit of vanadium.
Oh, see?
Manganese. What, helium and neon? Nope. Not unless you're like, okay. Oops. All right.
That's what I was
So here you go. Most of you, though, it's just oxygen, carbon, hydrogen, and nitrogen. Those four. Those four. That's 96% of you. It's oxygen, carbon, hydrogen, and nitrogen. And in fact, most of you is oxygen. Most, like 60% of the mass in your body is made up of oxygen. Yeah, okay, thank you.
I'm 60 point water. Gail said. Yeah.
What? You can measure how much.
It's like a Star Trek thing where they like do a body.
You have to be barefoot.
Wow,
How much
we entered.
oxygen you have?
What about these other things?
Oh,
Carbon, hydrogen, and nitrogen.
so nice.
Well, where does the carbon, the hydrogen, and the nitrogen
And that
come from?
air.
Food.
Yes, it comes from food and air. The carbon comes from our food. The hydrogen and nitrogen both mostly come from our food. What is this stuff? What is it? Are we just like piles of carbon and hydrogen and nitrogen?
We might be.
No, I want you guys to talk. Tell me what you think. What do you think it is? What is it that's making up all this? So Jacob rightly divined that oxygen is such a high percentage because we're mostly water, right? And what is water? H2O, right? But wait, that means there must be 2 times as much hydrogen as oxygen. Oxygen, wait. It does.
Oh my god, you guys. It's gonna be incredible.
It does. Remember, oxygen has atomic number 8, and the common isotope of it is oxygen 16. So which means oxygen is about 16 AMU, and hydrogen has an atomic number of what?
What?
1. Yeah, and so the most common isotope of hydrogen is the proton. So its atomic mass is about 1 AMU. So, yeah. Carbon is making up all of the non-water stuff. It's making up all the non-water stuff. Mhm. So if hydrogen is about 10% and oxygen is about 65%, but in water, there would be two hydrogens for every oxygen, which means there'd be about 2 AMUs or 2 units of mass of hydrogen to every 16 AMUs of oxygen. That would be a 1:8 ratio. This is not 1:8. This is 1:6 is what that is, right? 1:7 maybe. That extra hydrogen is attached to other things. Attached to other things in the body. And in fact, oxygen is in all water. Not all of this, 65%. Maybe this much of the oxygen is attached to other stuff, right? What is that other stuff? What is the other stuff that is where this carbon and all this nitrogen exist? Well, that's how we assimilate it. That's how we get it in. But what is it? What do we turn it into when it's inside of us? Any guesses? Why do we need nitrogen? You guys ever heard about that? It's to make these. It's to make these things here. The biomolecules of life is where those 4 are coming. So we make proteins out of carbon and nitrogen and oxygen and hydrogen. Carbohydrates are mostly just, as the name would suggest, a hydrated carbon. That's the empirical formula for a carbohydrate right there. And some of them have a little bit of nitrogen in them, but usually not that much. It's mostly. And then lipids, otherwise known as fats. Okay. And then nucleic acids. So lipids are pretty much just carbon, hydrogen, and oxygen. And then the nucleic acids. And we have the 4 characters. And then also, importantly, we have phosphorus. The phosphorus. And that is super duper important. There's only a little bit of phosphorus in your body, and it's pretty much all being used by the nucleic acids, but it's really important. We'll talk about that a little bit at some point. So these are the biomolecules of life. Yeah. And here is a way to look, to think about them. So this is the category, the 4 categories: carbohydrates, lipids, proteins, nucleic acids. And all of them are able to be built up into these chains, into these larger structures from smaller subunits. And that's what the smaller subunits are, what we call monomers. Mono meaning one. The monomers are built up into polymers. Poly meaning many, of course. So for sugars, the monomer is a monosaccharide, and it gets built into polysaccharides. For fats, for lipids, we have fatty acids and a molecule called glycerol that get made into, well, fat is not a very, but the real term should be triglycerides, and then phospholipids and phosphoglycerides, and glycerosphingolipids, all kinds of much bigger, more fun to say words. Amino acids are the fundamental building block of proteins, and they link up into chains and form polypeptides. Nucleotides are the fundamental unit that we make long chains, those helices of DNA, and then the folded structure. All right. So here? Yeah.
I mean, I don't know how it is.
Yeah.
You teach us.
Yeah. Yeah. Well,
You should teach everyone.
That was my goal initially. I wanted to teach every science at this at the school and build that
I was gonna
course.
say, 'cause then
And
like
so then I
you
could
would
hand
know
it.
what we.
I would know what you know, but then I could hand the built class over to somebody who could just teach it. Yeah, I didn't. I just did the upper level stuff. I never did any of the lower level stuff. Only so much. So I'm gonna, rather than taking the whole semester and diving in deep into what is really like a special area for me. I trained as a biochemist and I love it. I'm just going to give you a couple slides to give you a sense of what these biopolymers are. All right. So first, that first category, the protein category, we start at amino acids and we go through multiple steps of building bigger structures, and we eventually get to what are called proteins. In the middle here is this category called peptides. Peptides. So an amino acid, this structure that I have written here is a generic amino acid. And for an amino acid to be an amino acid, there's got to be an amine group on it. And when you see this here, this is a hydrogen, and this is meant to be a hydrogen as well. Man, that's a bad drawing. That's the amine. And then the other end is this organic acid. And when I say organic, the word organic does not mean that it wasn't sprayed with. The word organic, yeah, what? That's right. We are all organic life forms because we're made of carbon, right? So an organic acid is an acid that's based off of carbon. And this is the simplest organic acid, and it's called a carboxylic acid.
Does that mean that?
On Earth. Yes. Huh? There are people who think there may be silicon forms of life or life based off of boron or something like that on other planets. They've imagined that chemistry could exist in places where those elements, it's like Star Trek type stuff. But on Earth, we are organic or carbon-based life forms. So, yeah, what?
You have to have.
Yeah, on Earth, it's all oxygen, hydrogen, nitrogen. Yeah, there's nothing that's alive on Earth that doesn't. So to remind you, what is an acid? I maybe didn't give the best definition. I told you how we measure it. I talked about the pH scale, but I didn't really give you a succinct definition of acid. You want to try to give me one? Yeah. Sure. Yeah, that's a qualitative description. Yeah. That's good. What else can we do? How is it when that pH is going down? What do we actually measure? What's actually happening? What is pH? So let's go back. Huh? Let's go back this way. Skip all this stuff. Look at all this chemistry I skipped. Okay. Yeah. pH, it's the measure of acidity. It's the negative log of the proton concentration. Proton concentration. A single proton is what we call hydrogen, right? Ionized, it's H+. So an acid, let me write these down for you. In the context of this class, because there are broader definitions of an acid and base that will apply in other contexts, but within the bounds of this class, an acid, very simple, is a proton donor. It's some chemical that wants to ionize. It wants to unload a proton. It wants to dump a proton into solution. And the base is a proton acceptor. That's all. That's what an acid and a base is. It's a proton donor and a proton. Yes, absolutely.
So does that mean like is
You mean you're talking this way?
yeah is missing or not missing
Proton.
proton donor.
Yeah.
At least one less or
So, for example, vinegar. That's vinegar. Acetic acid. It's acetic acid. Looks like this. Are you just stretching back there, Jacob, or you have a question? You have a question? Please.
Okay, so is that why?
Hell yeah. Yeah, lemon juice does hurt when it goes in your eye. Because the acid that's in there, any acid is going to not feel especially good. Because it's at a different pH than the surface of the eye. Boric acid is okay to put in your eye because it's the same pH as the surface. Yeah. No, you used to be able to buy boric acid at the pharmacy to make a solution of it. There are still eye washes that, I don't know, you still can in some like old school pharmacies. I mean, that's just like an old way of doing things, and I don't know, people want packages that have exactly general loss of self-determination. Here is acetic acid. This is an acid, right? Because it has this proton that it would like to donate, and we can go from there. I'm just going to abbreviate this to CH3, and here's this. Okay? So this is the acetate ion. This is acetic acid. This is the acetate ion and the hydrogen ion. All right? So this is an acid. This is what's called the conjugate base. This right here. This guy is a conjugate base. It's a base because it's a proton acceptor. This arrow is actually two ways. In solution, vinegar is going backwards and forwards, right? So this proton over here, or maybe some other one over here, is like, hey, you lost your chance. I'm coming in. Hello. And it goes back and becomes acetic acid again. All right. An acid is just a molecule like this, where the equilibrium is driving much more this way than this way, so that it's dumping a bunch of protons into solution. So when you have vinegar, actually most of it is over here. All right, it's unloaded its proton. It's a proton donor. Vinegar, acetic acid, is an acid. It's a proton donor, and in solution, it unloads that proton, so that it increases the hydrogen ion concentration, thus lowering the pH. You guys follow all that? That's what an acid and a base is. Acid is proton donor, base is proton acceptor. And this is important just because that's how we're going to build protein. You had a question.
So does like lemon juice have in it like so I know like it's really bad for teeth. Take something from it or like is that why?
It's the citric acid, and citric acid is eating away at the enamel. It's an acid, And because of all of the hydrogen ion that's there from the citric acid, it eats away at just like you can etch in, like if you have a porcelain enameled sink and you leave acid sitting on it, with time it'll etch away and take away the brightness of the surface. It's also like people who are unfortunately afflicted with bulimia, type of where they those people have really poor dentition. Stomach acid, stomach significant vomiting a lot. The pH in the mouth is the way it. Okay. Anyways, acid and base, important concepts. Let's get back to some proteins. Look at all this stuff we went through so fast. Yeah, because amino acids, there are three things in its backbone. There's the amino group, the amine group, the carboxylic acid group, and there's this alpha carbon, which is the one. Alpha just means it's the first carbon away from the amine, which has this R group attached to it. And there's a whole bunch of them. There's like 20 different naturally occurring R groups. I'll show you a picture of it, but it doesn't really matter what the R group is. There's something decorating it, hanging off of it. But all of them look like this, all right? An amine can act as a base. Just like ammonia is a bit of a base, right? Your mom may or father may use ammonia to clean the floor or wipe a window. It's a base. It's basic. It's a proton acceptor. An amine is a proton acceptor because it likes nitrogen doesn't mind being like that. You can protonate an amine group and end up like that, where there's a charge on that nitrogen. Nitrogen doesn't mind holding a charge. So you can stick a third hydrogen on this amino group, and it'll be charged like that. That's fine. And I already told you carboxylic acid is an acid. So this amino acid has both an acid and a base in it. This is a weak acid. This is a weak base. Not super strong. The thing that's cool about it is that this this carboxylic acid can ionize itself. So here's this Zwitter ion where this has been ionized and this has been ionized. Both the amino group and the carboxylate group are ionized. And so now I can take one of these and link it up to the next. This carboxylate can attach to the amino group of another amino acid, and you can build these long chains of them. That's what peptides and eventually proteins. That's called the peptide bond. Anyways, these amino acids are what make up proteins, and we find them in all of these kinds of foods. So any kind of meat or animal product is going to have amino acids in it, but also, any kind of food is going to have some protein. But things that are high in protein are like beans and nuts. Different types of certain types of grains are pretty high in protein. Like I said, any kind of meat is going to have lots of protein. All right, sugars. So simple sugars, there's all kinds of sources of sugars, and sugars are super duper complex. I devoted 8 years to getting a PhD in carbohydrate. I only scratched the surface. So it's sugars are anything but simple, but we're going to give you a very simple overview. Simple sugars are these single monomers, and what a sugar is, like I said, it's a hydrated carbon. So you're going to have some carbon, some hydrogen, and oxygen in them, and it's in this ratio. For every carbon, there's going to be an H2O. And then the number of carbons is N. So this is glucose, and in glucose, N equals 6. 1, 2, 3, 4, 5, 6. And there's 6 oxygens, 1, 2, 3, 4, 5, 6. And there's 12 hydrogens. I won't count them, but take my word for it. There's 12. And then they can form this ring, etc. When you look at this, what do you notice? These hydrogens are attached to the oxygen, which is attached to the carbon. Does anyone know what this is called chemically? What that structure is called chemically? Like just this little part here? Like if I were to take this part of the molecule right here, that chunk, this 2-carbon chunk, with one OH group hanging off of it, so it would look like this, CH3, CH2OH. Here's the CH2 and then the OH. Does anyone know what that is? Alcohol, ethanol. That's actually beer, wine, whiskey, whatever. Pick your poison. So a sugar, these are called hydroxyl groups. The thing in alcohol that drives you crazy is the effect of the alcohol group. And so a sugar has all of these different alcohol groups all around it. And they're chemically related to alcohol. All right? But they have some unique differences. And I'm not going to get deep into it because it would take longer time to not lose you in the forest of describing that for me to build it up. But carbohydrates do a lot of things. Some of the basic stuff that you need to know is we burn them for fuel. These carbon-carbon bonds in here have energy. You've probably seen people burn alcohol lamps or go to a Greek restaurant and they do the saganaki. They pour the alcohol over the cheese and light it on fire. Opa, right? Yeah. Yeah. It has similar chemical functional groups. And the liver processes it in ways that are I literally teach a whole class of it. But yeah, so fermentation is the process whereby bacteria or yeast actually are going to break down sugars for energy, and instead of when we break down a carbohydrate, we're burning it. It's like a combustion reaction. In fact, here it is. It's C. Let's do it like this. C6H12O6. That's glucose. Leads to CO2 plus H2O, and we need to add some O2 to burn it with. We breathe in oxygen. This is, and let's balance our equation here. Yep. So 6. 12, 6. This chemical reaction is equally applied to you eating sugar, carbohydrates, a meal, breathing in oxygen, getting energy out. We'll put plus heat because heat comes out and your body uses that energy, and then you blow off the carbon dioxide in your breath as you exhale, and then there's some water that's made as a byproduct. Your body does this. This is the exact same reaction as when you take a chunk of wood and throw it on the fire. It starts burning, it releases heat, carbon dioxide, and a little water vapor, and it uses up oxygen. Wood is just a polymer of glucose. Wood is a long chain polymer of glucose that's called cellulose, which is wood fiber. Right. So this glucose, yeah. Have I lost you guys? Are we good? We're almost. I can get you to the end of this slide. Glucose gets packaged into this molecule called glycogen. Glycogen is what we call animal starch. So in a potato, you have something called amylose. That's vegetable starch. And it's very similar to glycogen. All these little dots here, these little beads, are glucose molecules that have been built up into a chain and attached to a little protein in the middle called glycogen. And this glycogen is stored in the liver and in your muscles. The glycogen in your muscles is so that you move your body around, and the glycogen that's stored in the liver is to keep your blood sugar stable so your brain will. All right? Glycogen. N-acetylated sugars, sugars that have nitrogen in them, are important for making things like cartilage. You've probably heard of glucosamine before. Your grandma maybe takes glucosamine. Joints. And glucose, this is glucosamine. It's just a glucose with an amine group. We know what an amine group looks like. We saw it on the amino acid. When it's attached to a glucose molecule, it becomes glucosamine. Glucosamine is important in making a bunch of things, one of them being. So those are, that's like a super brief introduction to sugar. So there are questions on either of those two things. The next one that we have is fatty acids, fats, and triglycerides. So normally I have like long lectures associated with one slide. See what they want, a sense of. A fatty acid, this is a fatty acid. It's an acid because it has that carboxylic acid, that organic acid that I talked about. Organic because it has carbon, and it's an acid. It's a proton donor. That hydrogen is ready to jump ship. It's because this carboxylate group, I'll draw this for you. This thing that is left over is actually in, it looks more like this. And those two oxygens sort of share the negative charge. So it's able to spread that negative charge out over a bigger chunk of the molecule. So that this carboxylate ion is pretty happy. So that's the acid part of it. Then the fat part of it is this bit over here, this long, greasy chain. There's nothing in here except carbon and hydrogen. Nothing at all. Carbon and hydrogen. It's hydrocarbon. So, for example, all of the stuff we're pumping out of the ground and sticking in our cars, the gasoline, those are essentially these. They're just hydrocarbons that are dead dinosaurs, old trees, stuff like that. That were fats that degraded, and all this, they were reduced. There's no oxygen in them anymore. They're just long, greasy chains that we stick in our cars and burn. There's a lot of energy in here, a lot of carbon-carbon bonds. In fact, fats are 2.5 times the energy density of a carbohydrate or a protein. The amount of energy that you get out by burning a fat is 2.5 times more than the energy you get out of burning the same mass of carbohydrate. Very energy efficient way of storing. Okay, that's class. Seems like, right? Yeah. That was some real stuff there. We covered some real stuff today. We'll come back next week Okay. And what do I want to talk about next week? I'll probably finish up triglycerides, and then I think I'm going to skip going into proteins in detail. For those of you who are interested in that, you can look those over. I'm going to move forward to homeostasis because I want to get onto physiology, organ systems, and homeostasis. That's what I'll do.
And
So